Here we're depicting two masses, M1 and M2. Maybe they're balls, maybe they're something else. They're approaching each other. Velocity of M1 is V1, velocity of M2 is V2, and those velocities are vectors. So let's go ahead and indicate that they are. And they come together and they exert equal and opposite forces on each other while they're in contact. Now those objects, whether you can see it or not, and for steel balls, for example, they don't compress much, but they do compress a little bit, and with a lot of force. So they compress a bit, and then they spring apart. So here they're shown as being compressed. I've kind of flattened out the contact surfaces. And then they spring apart, and at the instant they're apart, they have velocities V1 prime and V2 prime. Okay, now, if these objects are moving along the same straight line, then we don't need necessarily the vectors. We can treat these as scalar quantities, as plus or minus. They're not really scalars, they're still vectors because they have direction, positive or negative. Okay, now, the force exerted on object 1 by object 2, F12, and that's a vector, as is this vector, is depicted here, F21 depicted here. Those vectors by Newton's second law are equal and opposite. Newton's third law, they're equal and opposite. So, got a graph here. Kind of shows how the forces work. The forces are small at first contact, they peak, and then they fall off. Okay, just kind of like you compress a spring. When you hit the spring, it doesn't take much force, but the more you compress it, the more force it takes. Then it pushes back apart with less and less force. So you get something like this, a graph of the magnitude of the force versus time. And of course, both of these forces are equal, so they both have the same magnitude, but of course they're in opposite directions. Now we ask the question, what's the average force exerted? Because if we multiply the average force by delta T, it turns out that we're going to get the change in what we call the momentum. And we've seen this before when we plug A equals F over M into the second equation of uniformly accelerated motion, we immediately get the impulse momentum theorem. We've talked about that earlier. We'll repeat that here. But the point is that the impulse, which is equal to the change in momentum, is equal to the average force times the time interval. So let delta T be the interval. We ask, what is F average? What is the average force? Well, the average of any function is what you get when you integrate that function and divide by the length of the interval over which you integrate it. So the time average of the force, which is the one we're interested in here, is just the integral divided by delta T. The result being that the average force multiplied by delta T is equal to the integral of F dt. Now, the integral of F dt is equal to the area under this force curve. So the average force is the force which, acting over this time interval, gives us the same area as the curve. So if you look at this area here, look at the region above the rectangular region representing the average force for the interval. So here's F average. This rectangle has a certain area. If you take this peak up here, cut it in half, and paste half of it in this corner, half of it in this corner, is it plausible that you get that you can exactly fill these corners? Well, it's not plausible you could exactly do that, but this is not an implausible model. I think maybe the average force would have to be a little lower. The point being, again, that the area of this rectangle here should equal the total area under the curve. Okay, so There's a little more here. If we do this integral of f dt, and we know that integral is going to be equal to the average force times the delta t. If we do this integral, what are we integrating? We're integrating mass times acceleration. Now, if the mass is constant, what we get, we can just factor the mass out of the equation, and we get the mass multiplied by the integral of the acceleration with respect to t. Now, I haven't put limits on the integral. It's the integral over the interval delta t. So from some t1 to some t2, on that interval, the integral of a dt is going to be the change in velocity on that interval. So the integral of f dt is equal to the mass times the change in velocity. Okay? So f average delta t is the integral of f dt, and we call that the impulse of the force. M delta v is the change in what we call the momentum. So I'll make a little note here. mv equals momentum. Now take the chance and abbreviate the word momentum. So m delta v is the change in the momentum. So we have here that the impulse, integral of f dt, also equal to f average times the delta t, duration of the force, is equal to m delta v, which is the change in momentum. So we have these two quantities equal. That's our impulse momentum theorem.